Everyone, here's the review for Chapter 24 and 25, Capacitance and Direct Current. For capacitance, remember, capacitance was a source of potential difference. We could store charge in a location, we could separate them on the two plates, and due to the geometry of the plates, so the area between them, the distance between the plates, or if we use spherical or cylindrical capacitors, the capacitance is just the ability to store charge. It gives you a value of how much charge you could store per unit volt. So they have the equation rearranged here on your formula sheet of V equals Q over C, but you can rearrange it easily to solve for capacitance. The next one down there shows you that capacitance is equal to kappa epsilon 0 A over D. That's what we talked about, that the capacitance really depends on the geometry, how big you make the plates, how far away they are. Epsilon 0 is the permittivity of free space, and the last note down there is dielectrics. That's what the kappa is. Dielectrics will change your capacitance, increase the capacitance by you putting an insulator in between those two plates. We saw that there was energy stored in capacitors. We saw the generators spinning and powering light bulbs with the energy in a capacitor. You've got two of the three equations up there, the 1/2 QV and the 1/2 CV squared. That's the energy stored in a capacitor, not the energy provided by a battery. The energy provided by a battery would just be QV. So the amount of charge times the potential of a battery. But when it gets into the capacitor, we lose some of the energy upon trying to separate charges and put them on those plates. We then had capacitors hooked together in series and parallel. You can see that they give you the two equations for parallel capacitors and series capacitors. Parallel capacitors, you just add up all the capacitance, and series is that 1 over and all the fractions. So you get less and less capacitance when you're in series. Know the rules for series and parallel. The rules saying that we've got same volts in parallel and shared volts in series, and know how the charges react as well. We did scenarios when we had a capacitor and we were connected to a battery or disconnected to a battery. Remember what can change and what can't change. If we are connected to a battery, the voltage stays constant. If we're disconnected from a battery, the charge has to stay constant because we can't separate charges anymore. And we can affect capacitance by the areas and distances. We also connected capacitors to each other. So we charged up one capacitor and then had a second capacitor that was uncharged. Remember, they came to the same voltage, the same potential difference. So once you were able to do that, you were able to see how the charges redistribute themselves based on the two different containers. Which then took us into Chapter 25. Chapter 25, we've talked about storing charges and what they can do for us. We then wanted charges to move. And the reason charges move is that there's an electric field inside the wires pushing those charges through the wires. We saw that in what is happening in wires. Due to the size of a wire, we have a current density. That's what J is. That's current per unit area. That's not on your equation sheet, so that's one you'll have to remember. The flow of charge is dq dt, the amount of charge passing per second. We talked about how fast electrons actually move through the wire, and that's in the current equation over here with I equals NE VD times the area. VD being the drift velocity of those electrons. We found out the drift velocity was very, very slow for charges, but that's because you have an army of electrons that is moving through the wire, and one electron bumps into the next. The energy transfers through almost at the speed of light, but the individual charge in the switch does not make it into your light bulb very, very quickly. It takes a long time for that charge to actually move. Once we had moving charges, we looked at Ohm's law and the relationship between voltage, current, and the friction that a charge feels, the resistance. So more volts gives you more flow, but you increase that resistance, you're going to decrease the amount of charges that can move around the circuit. Once we had V equals IR, we then had the power equation. Power is the amount of energy dissipated into your circuit. It's either given off as heat, sound, or light, or how much energy a battery may be providing a circuit. So power is current times voltage, but remember, knowing Ohm's law, we can come up with three different power equations. We then put resistors in series and parallel, and just like capacitors, we see that resistors here in series actually are the sum, and in parallel it's the inverse, the 1 over the resistance. So more and more resistors in a series is harder to get through, but more and more resistors in parallel is a much easier path because everyone has their own connection back to the battery. The rules are kind of similar, In parallel, everybody still gets the same volts, and in series we all share the volts, but now the current is going to be either the same or split up depending on which branch you're talking about. We then put them in combinations where we had series and parallel combined, and we introduced Kirchhoff. Kirchhoff had two rules when you're going around any circuit, so if you don't want to just combine your circuit down into one, you can make loops, and with the loops you're trying to conserve energy by conserving all the voltage. The junction rule was trying to make sure that any charge going into a junction that splits off into many pieces is the same that comes out of that junction, so we can't create or destroy charge. And the last thing we did was charging and discharging RC circuits, resistors and capacitors. We found out that RC is the time constant, time for it to get to a certain amount of charge or discharge, and it was not a constant growth or discharge. It was an exponential growth or decay. So we did, the last two videos were all about the rate at which charges change on a capacitor and how the currents and voltages are affected in an RC circuit. Remember, they're going to talk about some of the times when the switch just closes after the switch has been closed a long time, and what happens when the switch is suddenly opened. So those are the things that AP likes to focus on. So these are the topics in the electricity section for capacitance and direct current. Good luck and happy studying.